This is video 4 of categorical analysis, and we will learn about the chi-square goodness of fit test. There are several statistical tests using chi-square distribution. Here, we will introduce a couple special cases. Chi-square goodness of fit test can be used when a variable has multiple categories, and we want to test if those categories follow the specific distribution. In this example, volunteers at a teen hotline have been assigned based on the assumption that 40% of all calls are drug-related, 25% are sex-related, 25% are stress-related, and 10% concerned educational issues. Each call is classified into one of these 4 categories based on the primary issue raised by the caller. The following data are collected from 120 randomly selected calls placed to the teen hotline. Based on the data, is the assumption regarding the distribution of topic issues appropriate? So literally, these numbers are representing 40, 25, 25, and 10% reasonably. Here we have one variable, which is the hotline call category with 4 different categories here: drug, sex, stress, and education. And want to test if the data follows the specific distribution: 40, 25, 25, and 10%. Chi-square goodness of fit test can be used. The null hypothesis for the chi-square goodness of fit test is the variable has the specific distribution, and the alternative hypothesis is the variable does not follow the specific distribution. In our example, the null hypothesis is the hotline call category distribution follows 40, 25, 25, and 10%. And the alternative hypothesis is that the distribution does not follow 40, 25, 25, and 10%. The test statistics is summation of the squared difference between observed value OI and expected value EI relative to the expected value EI. In the example, we can imagine the expected value can be calculated as the proportion of each category times the sample size. This means the expected value EIs are 40% of 120 calls for the drug-related, 25% of 120 calls for the sex and stress-related, and 10% of 120 calls for the educational issues. If the difference between observed value and expected value is large, if the numerator value is large, we will end up a larger number of test statistics and most likely to reject the null hypothesis. This larger chi-square value, we're gonna have more likely to reject null hypothesis. Theoretically, the sum of OI minus EI squared over EI follows chi-square distribution. Decision can be made using either chi-square table value, critical value here, or p-value that is calculated based on chi-square distribution. This slide shows how the calculation can be done to calculate the test statistics. Observed value and calculated expected value. Again, these are 120 times 0.4, 120 times 0.25, 120 times 0.25, and 120 times 0.1. And eventually, so you're gonna calculate the all observed minus expected, and then eventually you can calculate the OI minus EI squared over EI, and then the last column is sum of it, which is 5.92, which will be chi-square test statistics value. We don't usually do this by hand, but this step shows us the idea that the difference between the observed and expected value for each category that contributes to test statistics. Also, we can see which categories has the bigger difference numbers. In this example, stress-related, this one, 2.7, stress-related call category has the biggest difference between the observed and expected value. So probably this number contributes the chi-square number the most. In R, chi-square, so CHISQ dot test function do chi-square goodness of fit test. We first list the observed value. So N call is this number of observed value and the proportion of the specific distribution for P. So here are the values that we are comparing to. The result is shown below in the gray box. Oops. The test statistics is 5.9169, which is the same as our hand calculation in the previous slide. The degrees of freedom is the number of categories minus 1, which is 3 here. And the p-value is 0.1157, which is greater than our usual significance level, 0.05. Thus, we can conclude that the observed proportion are not significantly different from the expected proportion. There is no significant, statistically significant evidence to say that the hotline category distribution is different from 40%, 25%, 25%, and 10%.